Welcome to the Deep Dive, where we cut through the noise and get straight to the core of what you need to know about the most fascinating topics impacting our world. Today, we're plunging into something truly remarkable. Just think for a moment about modern AI. It recognizes faces in your photos with uncanny accuracy, translates languages instantly, and systems like AlphaGo have even beaten world champions at games like Go. These powerful systems feel almost magical, don't they? In their ability to perform incredibly complex tasks that seemed impossible just a few years ago.
It really is astounding to witness, and for many, it naturally raises a big question. What exactly makes all of this possible? It's far more than just clever algorithms, though those are certainly, a crucial part of it. There's this massive, largely unseen engine, a fundamental infrastructure that's quietly powering these groundbreaking capabilities behind the scenes.
Okay, so if it's far more than just algorithms, what is this unseen engine? Where do we even begin to unpack it? Our mission today is to take a deep dive into that very infrastructure. We're going to explore why today's most advanced AI effectively lives on the internet, deeply dependent on vast data storage, specialized computing power like graphics processing units or GPUs, and the sheer massive scale of cloud computing. We want to help you understand this unseen scaffolding that supports the entire AI revolution and what that means not just for the technology itself, but for its future and, well, for all of us.
Okay, let's unpack the first piece of this puzzle. When we look at the dramatic advances in AI over the past decade, and that includes everything from the image and facial recognition you mentioned to sophisticated language translation to AlphaGo's incredible conquest, the vast majority of these breakthroughs are powered by a technology called deep learning or deep neural networks. It truly is the primary engine driving this revolution.
And what's particularly fascinating about deep learning is that these aren't your typical computer programs, right? Not ones that just follow a few lines of explicit code like something you'd imagine from classic software. Deep learning systems are essentially programs that program themselves by looking at information, as one expert put it. So if traditional software is like giving a chef a precise recipe, deep learning is more like giving them millions of ingredients and photos of finished dishes and asking them to figure out the recipe themselves, gradually refining it with each attempt.
Exactly.
This process, as you can imagine, means they have an almost insatiable appetite for data. To train a robust deep learning model, you don't just need data. You need huge volumes of labeled training data.
That's precisely it. I mean, imagine trying to teach a system to recognize a cat. You can't just show it a handful of pictures. You'd need like thousands, possibly even millions of images of various categories, not just cats, but dogs, cars, trees, everything, so it learns the nuances. Take the famous ImageNet competition, for instance, which spurred huge progress in computer vision. It provided competitors with a staggering 1.2 million labeled training images. That's just a colossal amount of visual information for a system to learn from.
Yeah, 1.2 million differentiating everything from a Siamese cat to a tabby. And it's not just images or even simple data points. When we talk about real-world applications like using machine learning for drug discovery, researchers are now working with human cohort data sets. These data sets contain large amounts of high-quality measurements for hundreds of thousands of individuals. That means genetic information, medical records, lifestyle data, a truly immense volume of information that these systems devour to learn, find patterns, and become intelligent.
Yeah.
It's hard to overstate the scale. It's not just about having data. It's about having enough data, and often labeled data, which itself can be a massive undertaking.
Yeah, and that labeling part is crucial. This hunger for data is actually one of the biggest drivers of economic value in the AI space today. Data itself has become a new, incredibly valuable commodity. Now, processing these truly massive data sets and training such complex deep learning models isn't something your average computer can just, well, do. This brings us to where it gets really interesting. The computational intensity required is simply enormous. Your laptop, no matter how powerful it seems, just isn't built for this kind of heavy lifting. It's like trying to cook for 1,000 people in a tiny home kitchen.
Right, yeah. So with this unimaginable scale of data, my laptop's definitely out. What kind of power does it actually take to crunch all that? This is where graphics processing units, or GPUs, step into the spotlight. Historically, these were designed primarily for one thing: rendering complex graphics in video games. We all know them from that. But companies like NVIDIA and Intel have seen their entire businesses transformed as they rush to build hardware optimized for neural networks. The key here is the GPU's architecture, right? Unlike a central processing unit, or a CPU, which is designed for sequential, complex tasks, a GPU has thousands of smaller, more specialized cores. This makes them incredibly efficient at performing many simple calculations simultaneously.
Exactly. That parallel processing capability is the game changer.
Precisely the kind of matrix multiplications and parallel processing that neural networks require for training.
Precisely. It was a powerful convergence. The success of the 2012 ImageNet competition, for example, wasn't just about the ImageNet data or the breakthrough convolutional neural networks algorithm. Crucially, it was also about the timely emergence of powerful GPU computing power. This allowed researchers to process the vast ImageNet dataset in a way that simply wasn't feasible before. I mean, one of the early ambitious plans at Google Brain, a leading AI research team, was, and I quote, to use as much computation as we could throw at the problem to try to train neural networks.
Throwing computation at it.
Yeah, this wasn't about simply finding a single more powerful machine. It was about recognizing the inherent need for many, many powerful machines working in concert. To handle the sheer scale of the data and the complexity of these self-programming models, it ushered in an era where throwing computation at the problem became a viable and often necessary strategy.
Okay, so to summarize where we are, you've got these incredibly complex AI models that need millions, even hundreds of millions of data points. And they require specialized GPUs, not just one, but like lots of them, to train efficiently. How do you possibly manage that kind of infrastructure? Buying and maintaining thousands of GPUs in your own data center, dealing with power, cooling, constant upgrades. It sounds like a nightmare.
It absolutely is. And this is exactly why modern AI has found its natural, most effective home in the cloud. It's the only practical way to achieve the scale and flexibility needed without, building your own supercomputing center from scratch.
That makes total sense. It's the critical link.
That's the critical link. And what's truly fascinating is how Ray Kurzweil, a prominent AI thinker, observes this phenomenon. He points out that the cloud is doubling in power every year. It's not limited by a fixed enclosure, so the non-biological portion of our thinking will continue to grow. This really highlights the immense, flexible, and constantly growing capacity that cloud infrastructure provides. It's like an ever-expanding collective brain for AI.
An ever-expanding brain. I like that.
Instead of being constrained by the physical limits of a single building, cloud providers like Amazon Web Services, AWS, or Microsoft Azure can continuously add more servers, more GPUs, more storage, making their resources virtually limitless for individual users or companies.
And it's not just about raw power, is it? It's about effortless scalability and, well, ease of use. Jeff Dean of Google Brain explained their goal was to automatically map these large computations onto multiple computers in a relatively easy way that the programmer didn't have to specify.
Yeah.
This is precisely what cloud computing offers, right? The ability to scale up or down your computational resources on demand. Without you having to buy, install, and manage physical hardware yourself, you just ask for what you need.
Exactly. Need 100 GPUs for an hour? Fine. Need petabytes of storage for a year? You got it.
Yeah, the cloud provides it. This means you can run experiments that would be prohibitively expensive or just too complex to set up on your own. It lets you innovate at incredible speeds.
And this infrastructure has a profound effect on sort of democratizing AI development. Take TensorFlow, for instance. It's a huge open source software package, widely used for deep learning. While you can run these models on your laptop, you can run them on a machine with GPU cards that you bought. You can run them on a Raspberry Pi on Android, so it's versatile. But Google, a major player in AI and the creator of TensorFlow, explicitly states, we want our cloud to be the best place to run TensorFlow programs.
Makes sense from their perspective.
Yeah, and it isn't just marketing speak. It shows how cloud providers are actively building environments specifically designed to support AI development and deployment. They offer pre-configured virtual machines with GPUs, specialized AI services, simplified tools, making it far easier for a broader range of users, from individual researchers to small startups, to access this powerful technology without needing a huge upfront investment in hardware.
And the cloud really accelerates rapid experimentation too, doesn't it? Like those Automata products, for example. These are designed for people who might not have deep machine learning expertise. They basically repeatedly try lots and lots of machine learning experiments as a human machine learning expert would, but without you having to be a machine learning expert.
You give it your data, tell it the goal.
And it just goes off and automatically trains hundreds of thousands of models to find the best one. All possible because of that massive on-demand compute power in the cloud. It essentially takes the grunt work out of AI development for many applications, giving you a high-accuracy model without requiring you to be that deep expert yourself.
So what does this all mean for you, the everyday user, whether you realize it or not? This cloud-based infrastructure ensures that the AI services you rely on can be constantly updated and improved behind the scenes. The seamless image recognition on your phone that sorts your vacation photos, the voice assistants that answer your questions and understand your commands, the increasingly sophisticated applications you interact with daily, they're all running on this massive distributed computing power working tirelessly.
It's why AI capabilities feel like they're improving all the time, often with no visible software update on your end. The magic is just happening in the cloud.
Precisely.
So let's recap. We've seen how the incredible capabilities of modern AI are deeply rooted in this foundation of enormous labeled data sets, specialized hardware like GPUs, and the scalable, flexible power of cloud computing. This combination allows AI models to train on massive amounts of information and perform complex tasks that would be impossible otherwise. It really is the unseen scaffolding that supports the entire AI revolution, making it accessible and rapidly evolving.
And this concentration of immense resources in the cloud, mostly by a relatively small number of companies, the hyperscalers like AWS, Azure, and Google Cloud, it certainly drives incredible innovation and makes AI more accessible in many ways, no doubt about that. But it also raises an important question for the future, I think. Who controls and who ultimately has access to this incredibly transformative power?
That's a really crucial point. If the infrastructure for the most advanced AI is concentrated like that, how might this shape the future of knowledge itself, the development of new capabilities, and even broader societal power dynamics for everyone? It's definitely a thought worth mulling over, particularly as AI continues its rapid evolution, becoming an ever more integral part of our lives.